All right, so in this video, I'm going to be doing the logistic differential equations homework. Okay, so we're going to start off with this question about a number of frogs living in a pond. Let's see. Satisfies the logistic differential equation dy dt is 1/2500th of y times 1010 minus y. Okay, so what I know for a fact, just looking at this differential equation, is that the carrying capacity is 1010. And you can kind of see that right here on the slope field. Okay. So we want to sketch the solution curve that passes through the point 0 and 250. Okay, and so we know what this is going to look like. It's going to have, kind of an S shape, and it's going to need to approach that horizontal asymptote. And I need to also point out, we probably want to make sure we got a point of inflection around 505. It doesn't have to be perfect though, right? In general, we're just kind of following the lay of the land, going through the point they gave us. Next, we want to sketch the solution curve that passes through the point 0 and 1500. Well, we know that's where we've dropped too many frogs in the pond. The pond can't support that many frogs, and so, we're going to see some of them die off. Okay, and that's what we want to do there. Okay, if b is equal to 250, what is the largest rate of increase in the number of frogs in the pond? Well, if the initial population is positive but less than half of the carrying capacity, the maximum growth rate the maximum value of dy dt happens at y equals half of 1010. And so that's going to be 505. The actual largest rate of increase is where I plug in 505 and get dy dt. So the value of dy dt at the point where y equals 505 is going to be equal to, I'm just going to plug it in, 1/2500 times y is 505, and 1010 minus y is also going to be 505. Okay. Explain my reasoning, that was what I did up above, and indicate units of measure. Okay, well now I need to look and see, what are the units of dy dt? All right, well, okay, y is the number of frogs, t is measured in weeks, so the derivative of y with respect to t will be frogs per week. Okay.
Why is the number of frogs?
Cool. All right, if b is equal to 750, right, so if we start there, what's going to happen? Well, the largest rate of increase, if we start out over half the carrying capacity, is going to be just right at the beginning. Because what it's going to look like is, if this is 1010, and we start off pretty close, well, it's like an S curve, but the, whoops, can't see that. It's like an S curve, but the, most of the S has already happened. So it's really just going to kind of approach like this. And if it approaches like that, the steepest that this curve is going to be is right here at the beginning. So I'll say since f of 0 is between half of L and L, conclude that the maximum value of dy dt happens at t equals 0. Okay, and then the actual value is going to be dy dt at t equals 0. Well, at t equals 0, we know that dy dt depends on y, and so we know that at t equals 0, y is going to be 750. And so 1/2500 times 750 times, okay, I don't know just right off the top of my head. I think it's going to be 260, but not worth it, right? 1010 minus 750. And I'll just say frogs per week. All right? All right. Let b equal 100. Use Euler's method starting at t equals 0 with 2 steps of equal size to approximate f of 4, the number of frogs in the pond at time t equals 4 weeks. All right. Well, we will definitely show the computations because that's all Euler's method is, right? We know that. So I'm going to say, okay, starting at t equals 0, going to t equals 4, 2 steps of equal size. My first step will be t equals 2. Okay. I'm going to just kind of copy down the differential equation. All right. So the first tangent line for Euler's method is going to have a point, well, t equals 0 and y is 100. Slope is going to be y prime when I plug in 100 for y. So that's 100 times 910. So that's 91,000. Divide by 2,500. Okay, I don't remember, but I gotta assume that this was originally a calculator question because I don't think that's really within the realm of arithmetic we're expected to do in this class. So I'm gonna, bring out some technology. 91,000 divided by 2,500, and that's 36.4. Okay, yeah, that doesn't seem like something I'm supposed to be able to get on my own.
Yes.
All right, so my equation is y minus 100 is equal to 36.4 times t minus 0. All right, then I'll plug in to get an approximation.
Why am I so bad?
That would be y of 2 approximately equal to 100 plus 36.4 times 2 minus 0. Okay, so that's going to be 72.8. That's going to be 172.8. Okay, then my new point is going to be t equals 2 and y is 172.8. All right, need a little more. I don't know what to do here. Yeah, I'll just keep scrolling this on down. And I'm going to need a second tangent line. And that will be, okay, I've got my point. 2 and 177, wait, no, it's 172.8. The slope, yeah, if I have to plug this in to that formula, there's no way I'm going to be able to do that with my level of arithmetic. So what I'm going to do is I'm just going to make a fraction bar. I'll say y is 172.8 times 1010 minus 172.8. And then I'm going to divide by 2,500, and I'll have 57.867. All right, so the equation is going to be y minus 172.8 equals 57.867 times t minus 2. All right, so my approximation would be that y of 4 is approximately equal to 172.8 plus 57.867 times 4 minus 2 is 2. Now again, like I told you probably in the video, in the lesson, whenever you got this from me, is that if it's 2 steps of equal size, right, this number here, when we do the approximation, needs to be the same as that, right? Step size of 2. All right, and which you get a step size of 2 from 2 steps of equal width covering 0 to 4. They didn't tell you that in the statement of the question. Okay, and this is a safe place to stop. okay, on the free response section of an AP exam. Right? This is a number that's equivalent to the right answer. I will just, kind of plus 172.8. Yeah, that's going to be 288.534 or 535.
So I just wrong.
And like, you don't look at them. And so basically, it goes in around.
And that's my approximation using Euler's method for the number of frogs at time t equals 4 weeks. All right, what else do they have? Oh, wait, whoops. Determine whether the approximation found in part D is an underestimate or an overestimate for the true number of frogs in the pond at time t equals 4 when b equals 100. Explain my reasoning. Okay, well, okay. So for y between 100 and, say, 288, well, really, I guess it's 505. The second derivative of y with respect to t both times is positive. We know that because, well, this is kind of one of the things we know about logistic differential equation is the shape of the curve. Also, look over here. It's pretty clearly the slope is increasing. So it's going to be concave up. Okay? And if we've got concave up, then a tangent line sits underneath it. Whoops, can't see that. A tangent line sits underneath. Now, what really is happening is we're taking two tangent lines, and, can kind of do something like that. But even still, repeated tangent line approximations will still be underestimates because the curve is concave up. And therefore, a linear estimation, or a linear approximation, underestimates y of 4, f of 4, whatever they're saying. Okay? Okay, and that's the first page. All right. Okay, this one, the certain rumor. 3y times 1 minus y, where y is the proportion of the population that has heard the rumor at time t. Okay, so that means that 1 is the carrying capacity because that's 100% of people having heard the rumor. What proportion of the population has heard the rumor when it is spreading the fastest? 50%. No justification required for that, right? We don't need to take the derivative of dy dt with respect to y and show it's equal to 0 when y is equal to 0.5. That's not going to be the thing we need to do, right? They just accept that everyone knows that in a logistic differential equation scenario, the maximum growth rate happens at half the carrying capacity. Find the limit as t approaches infinity of y of t. That's the carrying capacity. We see that right here. It's equal to 1. Again, no justification required for the things that they just assume that we know about logistic differential equations, that we can find the carrying capacity right here, and the carrying capacity is the limit as t approaches infinity of the solution to that logistic differential equation. Okay, now use separation of variables to find y equals f of t. The particular solution with y of 0 is 0.1. This is going to be a little rough, okay, but it's going to be all right. It's something we can definitely do. We're just going to have to use separation of variables and a partial fraction decomposition. But I put a bunch of room here. I'm not scared. I'm just going to copy the differential equation. dy dt is 3y times 1 minus y. And I'm going to leave the 3 on the right side and divide by the y and the 1 minus y. Okay? And you might be tempted to try to distribute that and then divide over, but we don't want to deal with second degree in a denominator for an integral situation. It's not what we want. So I'm going to have 1 over y times 1 minus y dy equals 3 dt. And I don't know, maybe you remember that when the denominator of a fraction you're trying to integrate is factorable, that's when we're going to do partial fractions. So maybe I'll do that over here to the left. Oh, I've got room. Just need to kind of scroll this a little. And I will say, all right, 1 over
She did. I put, and she got a piece of
y times 1 minus y is some number divided by y plus some other number divided by 1 minus y. Okay. What I'll say is that I know that 1 is going to be a times 1 minus y plus b times y. And I'm going to say let y equal 0 first, so that thing goes away. A, or 1, is equal to a times 1. So that means a is equal to 1. That's kind of nice. And then we're going to let y equal 1. That means that 1 is equal to b times 1, and that means b is 1. Okay. Now what I can do is I can say that this is the same as 1 over y plus 1 over 1 minus y dy, something I can integrate much easier, is equal to integral of 3 dt. Okay, we can do this. This is going to be log absolute value of y minus log absolute value of 1 minus y. Okay, I have minus here because of the chain rule with this thing, right? If we think about taking the derivative of this log, I'm going to have 1 over 1 minus y times the derivative of 1 minus y, which is negative 1. Okay, so in order to prepare for that, I need to put a negative here so that when I do take the derivative using the chain rule and multiply by that negative, I have plus 1 over 1 minus y. And that's going to be 3t plus c. Okay, let's say that, okay, I don't really know that I like where this is going as far as finding the c, so I'm going to combine these using a log property. I really don't think that should be too big of a deal. Not really going to change the difficulty of my computation in finding y over 1 minus y, absolute value, equals 3t plus c. These are the same. This is just a property of logarithms. Okay. Now, if I plug in 0.1 for y, let's just, this is supposed to be a no calculator question, but let's just kind of see what's going to happen here. 0.1 divided by 1 minus 0.1 is going to be 0.9, is going to be 1/9. Oh, I can see that, obviously. All right. Well, so that's the log of 1/9 is equal to 0 plus c. Oh, actually, no, that is going to be good. Okay, so I'm going to go over here and try to solve for my c. Log of 0.1 over 0.9, that's log of 1/9, is equal to 3 times 0 plus c, meaning that c is log of 1/9. Okay, now I'm going to take e to, so I'm going to have absolute value of y over 1 minus y equaling e to the 3t plus log of 9, log of 1/9. So that is going to be 1/9 e to the 3t. And you can believe me on that, or you can just go and work through it yourself. Now, really interested in how I'm going to deal with this, but maybe, I don't know. I'm just going to try to just figure it out, I guess. And wait a second, did I need this? I don't think I did, and so I think this is going to be positive. This is, again, very approximate. I really am of the opinion that they would not ask you to do this nowadays. This is a pretty old question. So, I know what I'm going to do. I'm going to flip this. I'm going to take both sides to the -1 power. That's definitely the thing to do. So 1 minus y over y is equal to 9e to the -3t, right? Just make everything flipped, or negative exponent. Then this here is equal to 1 over y minus 1. So now, yeah, this was definitely the thing to do. So 1 over y is equal to 1 plus 9e to the -3t. Therefore, y is equal to 1 over 1 plus 9e to the -3t. That's just about the most intense separation of variables problem I've seen for Cal BC. That was a lot of algebra, pretty heavy. gotta think that if you were expected to do separation of variables on your AP exam, it would not be a differential equation like this, okay? But it is something that we can do, you know? We can solve the logistic differential equation using separation of variables if we have to. But we really don't want to. Okay, which of these differential equations could model the logistic growth shown in the figure below? Well, basically all they've told us is that the carrying capacity is 200. So what I'm going to need to do, I know that the logistic differential equation has the form dp dt is kp times L minus p. But that's basically, right, some number of p's and some other number of p squared subtracted. So based on that, I'm going to go ahead and eliminate answer choices C, D, and E, right? So I've got it down to 2, and, well, in a multiple choice scenario, if we can get it down to 50-50, we got a pretty good chance, right? Because if we get 50% of the points on the AP Calculus exam, we're getting credit. So I'm going to go over here, but we can do better than just guessing, right? We can just factor out. What we're going to want to do is factor against that p squared, because then we'll just get 1p left here. So I'm going to factor out the 1 over 1,000. So for answer choice A, I'm factoring out 1,000th, which is like multiplying everything by 1,000. So 1,000 times 0.2 is 200. So factoring out the 1/1000th, and probably a power of p, right, because there's 2 of them there, and 1 here, I'm going to be left with 200 minus p. Okay, so that looks like it's got a carrying capacity of 200, and that's going to be the right answer. Okay, but I want to just show you why B is not the right answer, so I'm going to do the exact same thing. So if I was multiplying by, or if I was factoring out a 1/1000th, I'm really multiplying by 1,000, that's 100 minus P. Okay, but that's not the carrying capacity, right? That's the carrying capacity. So it's going to be answer choice A. All right, population P changes at a rate modeled by the differential equation. dp dt is 0.4 P times 3,000 minus P. Population increasing is going to be dp dt is positive. The rate is decreasing, the rate is dp dt. So if the is decreasing, that means its derivative is less than 0. So where is this thing increasing while concave down is kind of the question. Well, we know that the only place where it can be increasing and concave up is down here, right? Is underneath half the carrying capacity. And then, I don't know, that wasn't the very best sketch ever. But I'm going to say, wait. I don't want increasing at an increasing rate. I want increasing while frowning, right? Concave down. Okay, so that's going to be half of L to L, so that'll be 1,500 to 3,000.
King is 3, ace is 4.
Close. Better.
All right. Rate of change of the number of people in the grocery store is modeled by a logistic differential equation. The maximum number of people allowed. Okay, and then we're going, I see where this is headed. We're going to try to write the differential equation to describe this situation. So we know the form. Right? And so our job is to just figure out what is L and what is K. Well, they just told me right off the bat what L is. L is 500. So I'm going to maybe just actually make that happen. So 500 minus P. And this is actually a pretty common type of question that I've seen. I mean, it's usually multiple choice. Which of these differential equations describes the situation? And you just have to check that, you know, when you plug in P equals 100, you get dp dt equals 200, right? Now, we're going to have to do a little more work to find that, but that's fine. We can do that, because all we need to find is this K right here. So what I'm going to do is I'm going to say dp dt is 200 when P is 100. So 200 is K times 100 times 500 minus 100 is 400. Okay, that's 40,000. K is 200 divided by 40,000. How about we leave it, instead of 40,000, we call it 100 and 400. And that is going to give me 1 over 200. Okay, so I've got dp dt is 1/200th of p times 500 minus p. Okay. Then, all right, the number of moose in the national park is modeled by the function m that satisfies the logistic equation like that. What is the limit of m of t? Okay, well, the limit of m of t is the horizontal asymptote on the graph of m of t. That's the carrying capacity. Okay, now you may be already to the point where you know that it's going to just be this number and the answer is just 200. And I think you're good to say that without any justification. Maybe you're not sufficiently convinced. Maybe you need a little more evidence. What I'm going to do is I'm going to factor out a 1 over 200. And like I said before, if we're factoring out a 3 from something, what we're really doing is we're dividing each of the terms by 3. So if I'm factoring out a 1 over 200, I'm just going to be dividing everything by 1 over 200, which is like multiplying everything by 200. So 0.6 m times 200 times, I'm factoring out a, wait, what was I factoring out? I was factoring out a 1 over 200. Hold on, let's make this look a little nicer, yeah. 1 over 200 times 200 minus m. And just try to think about, distributing that back in. That'd be 1 m over 200. And then this is just 0.6 divided by 200. This is some other number times m times 200 minus m. That's the carrying capacity. M of t equals 200. And that's it, right? All right, that's all I got for you for this one. Let me know if you have any